Hi everyone and welcome to this new class in performance and specifically Breguet equations. So we will do a bit of an overview of these Breguet equations, okay? And my idea is actually to introduce some of mathematical concepts which are useful to the optimization of a specific aircraft, right? So this class, I advance you this, is a bit more mathematically oriented, but however it's kind of an overview of some different topics that we have covered already in order for you to see that they can be applied directly to the performance and to the optimization of performance of an aircraft. Now, let's start. Breguet equations are mathematical models which will relate a range of an aircraft, so the distance an aircraft can travel, to other parameters, such as geometry of the wings on flight conditions, for instance. It is usually used to visualize which optimizations can be done to the performance of the aircraft, okay? And how to design the aircraft to fulfill a given range. So it's kind of a way to relate the geometry of an aircraft in general terms and flight conditions to the actual range or capability, okay, of the aircraft itself. This mathematical derivation, okay, of these equations is actually quite straightforward, and it can be used as a first approximation of the optimization of the whole aircraft. Now, if you want to derive mathematically the different equations that we will see, you can just look for them, or you can ask me, and I'll try to find the exact derivation in some paper or another. It usually is not difficult to follow, okay, so you'll probably get it all right. In this case, I just wanted you to visualize the equations themselves, okay? So, we'll in fact study basically the range equation, the range Breguet equation, which is just defined as a distance. You know that the range is a distance, so a distance is equal to a velocity. In this case, it's the velocity of the aircraft multiplied by the time which we'll be flying, right? So the range is equivalent to the velocity of the aircraft times the time of flight. So the idea is, in order to optimize the range, we have to optimize these parameters, right? And optimizing this is actually the same as optimizing this, right? Because the flight time can be defined after some mathematical derivation as the ratio between the lift and drag, the specific impulse, and this function which is the Napoleon logarithm of the relation between the initial mass, initial weight, and final weight of the aircraft. Now, it's interesting to note that in order to optimize the range, what we will have to do is actually optimize this product. And in this case, we'll just focus on optimizing the flight time, right? So this would be optimizing these elements over here. Now, optimizing the flight time implies, by optimizing, I mean increasing as much as possible. So if we want a bigger range, what we have to do is actually increase the flight time, right? So basically we need to increase as much as possible, or have the biggest number, okay, as an outcome of these multiplications. And by this, what I mean is we need to maximize the lift to drag ratio, we need to maximize the specific impulse, and we need to maximize the Napoleon logarithm of the ratio between the initial weight and final weight. Now, let's start by maximizing the lift to drag ratio. This ratio will actually depend on the wing design. As we saw, airfoils are the way to relate the lift and drag. And in this case, what we'll do is actually discuss the polar curve, which is a curve which relates the coefficient of lift and coefficient of drag for different angles of attack. Okay, so the idea is just, you know, to evaluate the value of a coefficient of lift at a certain angle of attack and evaluate the coefficient of drag at the same angle of attack. And by evaluating the different coefficient of lifts and drag as following the angle of attack, we actually get a curve of all the ratios between the lift and drag. Now, what's interesting in this is that you can actually get a minimum drag coefficient of drag, right? So you can actually get the smallest value of drag, which would be something like this. You can see that because we have a curve which is defined by coefficient of lift and coefficient of drag, this is the minimum since the coefficient of drag is this axis over here, right? So it's like the first value that we get, the smallest value that we get with the coefficient of drag. Now, what I wanted to say is that if we want to maximize lift versus drag, it is quite intuitive that we need the smallest drag and the biggest lift. So we could actually focus on minimum drag as the maximum lift to drag ratio. But this is not the case, okay? It's quite interesting to note that this is the value for 6 degrees of angle of attack is actually the value of maximum lift to drag ratio. Even if the coefficient of drag is not the smallest, this actually gives the most the biggest value, the maximized value of the coefficient of lift divided by coefficient of drag. You can actually see it in this curve over here. It's actually the same. This curve is actually the same, but you actually get directly the lift to drag ratio as a function of the angle of attack, right? So here we have the angle of attack, which is implicit. We just calculate it, and we have this curve relating coefficient of lift and coefficient of drag. And in this case, we directly get the lift to drag ratio, which is equal to the coefficient of lift divided by the coefficient of drag, to angle of attack, right? So we just get the curve itself. And as you can see, for minimum drag, we get a value, but it's not optimal. It's not the best one in terms of lift to drag ratio. This would be the most, the biggest ratio between lift and drag, okay, for 6 degrees of angle of attack. Now, the idea then is that we have to design the wing. Of course, the wing will actually provide this curve, okay, but what we have to do is ensure that our aircraft will actually be flying at this specific point, because at this point we will have maximum efficiency in terms of lift to drag ratio, and therefore we will have optimized our flight time. So it's important to take into account that this parameter actually depends on the wing design, but also depends on the flight conditions as a function of the angle of attack. Okay, what else? What we need to do also is maximize the specific impulse of our engine. Now, as I mentioned, this depends on the engine design. This case depends on the wing design, and the specific impulse depends on the engine design. Now, specific impulse is a definition, okay, it's just a mathematical definition almost, in order to measure the engine efficiency, and is just related to the effective velocity of ejection, the increase of the velocity due to the air going through the engine, okay? So basically we have just the aircraft, the total aircraft, which is traveling at a certain speed. So we have a relative speed between the wind and the engine, okay, which would be this speed over here. And because we have the engine and we actually get more power, we get thrust from the engine, then the exhaust velocity, which means the velocity at which the air or the wind is actually getting out of the engine, is actually bigger than the relative velocity of the wind with respect to the engine, okay? So we just get more velocity due to the air going through the engine, right? So specific impulse is just a measure. It is multiplied by a constant, but it's just a measure of the relative velocity increase, okay? So in this case, you can see that all of this velocity would be the velocity at the end, and this velocity is the initial velocity. You just make the calculation of the difference, okay, between exhaust velocity and initial velocity, and you get kind of the specific impulse. So you can see that the specific impulse depends on the engine design as a way to define at which velocity the exhaust velocity is actually going at, okay? So it's just a measure of how much the engine is able to accelerate the fluid through the engine, right? So this is the specific impulse. It's just kind of an efficiency for the engine itself. What else? What we need to do also is maximize this function over here, which is the Napierian logarithm of the weight, the initial weight and the final weight. Now, this will depend on structural design, basically. And what this means is that basically, if we want to maximize this function over here, it is equal to maximizing, okay, all of this here. Now let's see this. This is the initial weight and this is the final weight. So initial weight will be actually the same as the final weight plus the fuel, right? Because throughout the flight we actually consume some of this fuel. So initially we will have the same weight as finally, but with also the fuel, right? So yeah, the idea is that the difference between the initial weight and the final weight is just the amount of fuel that we had before and which we have consumed or used in order to propel our engine, right? So in a way you can actually, mathematically you can see that this term cancels with this one, right? But we still have the weight of the fuel divided by the final weight of the aircraft, right? And so what this means is that we actually get the Napoleon logarithm of this function over here. Right, so imagine that we had no fuel at all. If we have no fuel, okay, this would imply that this is 0, right, because we have no weight of the fuel. And if this is 0, then this is the logarithm, the Napoleon logarithm of 1. And if we go to this, which is the function of the logarithm, the Napoleon logarithm, okay, this is the the geometry of this function, we can see that for a given x would be 1, right, because this we said is 0. If we consider that there's no fuel, we would actually get the result of 0. So in this case, this equation, in the case that we have no fuel, actually is stating that this is 0, so all of this is 0, and therefore the flight time is 0. Does this make sense? Well, it kind of does, doesn't it? Because it means that if we have no fuel, then the flight time is 0. Well, that's kind of, it's an interesting analysis of this mathematical form. Now, let's see the most generic case, which is to have some fuel, okay? And the relation between the fuel and the final weight is actually important in terms of how much we can actually maximize the flight time. Now, in order to maximize this function, which is what we want to do, we have to maximize this function over here. And as you can see, this function, which is the Napoleon logarithm, is actually increases with the amount of fuel that we put, right? Because if the fuel is, say, 1/10 of the final weight, then this coefficient would be 0.1, right? So we would have 1 plus 0.1, and this would be 1.1. So the Napoleon logarithm of 1.1, we can go to this graph, would actually be this value over here. However, if we have almost, say, 50% of the total weight of our aircraft is actually fuel, which is improbable, but just a theoretical model, then this means that this over here would be 0.5, because the amount of weight of the fuel is actually 50% of the total final weight. So this relation would be 0.5. If we add 1 plus 0.5, this is equal to 1.5, and 1.5 would be over here, and you can see that the function is very much higher. So in the end, what we have to optimize is the weight fuel divided by the final weight, which in other terms means optimizing the amount of fuel that we have with respect to the total mass of the aircraft. So another way of seeing this is that we need to decrease as much as possible the final weight in order for the fuel to be an important factor with respect to the final weight. So the solution of this is actually to decrease as much as possible the final weight. And this is why this will depend on the structural design. So we need a structural design which is as light as possible. And it kind of makes sense too, right? So the flight time will be higher if our aircraft has actually less mass. Then that kind of makes sense, because if the mass is very high for the aircraft, you can imagine intuitively that the flight time will be smaller. So this is the idea, okay? Optimize this ratio over here, which means decreasing as much as possible the final weight, and so decreasing the structural mass of the aircraft. This is what you need to know. Okay, so as a summary of what we saw, in order to optimize the range, what we have to do is optimize the flight time, which means maximizing the lift to drag ratio, maximize specific impulse, and maximize this factor over here. Okay, so basically we have to design a high lift to drag ratio wing. Okay, so it is important to study which airfoil and 3D configuration will give us the best ratio. Also, we need to have a high velocity of ejection for the engines, which we discussed for the specific impulse. So high compression ratios is actually very important in the design of the engine and will affect how much velocity we can actually get out of the engine. So as I mentioned, high compression ratios in the compressor and high temperature fluid due to the combustion chamber. That's what we need. High temperature fluid and high compression ratios. So combustion chamber has to be effective, and also the compressor has to pressurize the air in a big way. Okay, we need a big compression. Also, as we mentioned, maximizing the ratio between fuel mass and aircraft mass. So basically studying how to reduce the mass of the structure of the aircraft. Right, so I think this is all for the Breguet equation of range. As always, if you have any doubts, if you want to have more insight into the Breguet equation or any other topics, just let me know.